Okay, wonderful. We have the recording started up. A quick remark here. I did post some sample exam solutions this morning. Today we fixed a small problem in one of the solutions, and so hopefully we've rooted out all the errors. So just letting you know those solutions are available in the folder for the sample final exam. Okay, let's begin by resuming a calculation we were doing last time. So what we did last time, here are some notes from our last meeting. I'll position it like this. So you can see we're interested in moving towards a discussion of the Lagrange points. These are some very special points in space. And we've talked about exciting applications such as the interplanetary superhighway. Okay. To appreciate what's going on with the Lagrange points, we revisited this problem with the simple pendulum, okay? And so you see the horizontal axis here is the phi axis. The vertical axis is the phi dot axis. So this is the classical state space. We have phi and phi dot for the simple pendulum. We have a restoring force, proportional to the sine. So there's that nonlinear aspect to the problem. This is the classical state space, so that's the title for this diagram. And we observed that the value of the Hamiltonian is constant. It is meaningful to talk about the Hamiltonian as we did in chapter 7. We had a Hamiltonian. It was a function of generalized coordinates and q dots. So it was a function of q's and q dots in chapter 7, a perfectly good function defined on the classical state space, okay? And we saw that the constancy of the Hamiltonian, right, which is often expressed as dH dt, excuse me, right, this is 0, expressing the fact that the Hamiltonian is constant along an orbit. It is not correct to say that the Hamiltonian is a global constant. So I'll include that here parenthetically. H is not a global okay. So you see, when people say that the Hamiltonian is a constant, that would not be correct in a very important context that's part of this discussion, which is we have this Hamiltonian as a function defined on this two-dimensional space, this picture here, the state space. Now that Hamiltonian is not a constant like 5 joules across the entire picture. It is a constant along each one of these curves. It's a different constant for different curves. Okay, so that's the important distinction. And when we have this notation, so this is the ordinary ddt, that's the total time derivative. The phrase that's used in classical mechanics is the Hamiltonian is constant along an orbit. So if you choose one of these curves, that's an orbit, and that includes the so-called rolling motion of the pendulum. This is the term orbit in classical mechanics. The value of the Hamiltonian is constant along any one of these curves, okay? But it's a different constant for different curves. And so it's not correct to say that the Hamiltonian is simply a global constant. If it were, Hamilton's equation would give you a 0 and a 0 for those partial derivatives, right? Okay, anyways, that's a quick review of this picture. Now, the picture, again, shows you the streamlines, right? These are the so-called streamlines. These are lines that are everywhere tangent to the vector field. We haven't shown the vector field. We would be drawing a whole bunch of arrows all over this picture if we want to draw the vector field. But the existence of that vector field is very important to us. That's the so-called Hamiltonian vector field. And there are courses over in the math department devoted to, in some cases, some aspects of classical physics. And they're always talking about Hamiltonian vector fields. Right? And on the homework, we had this two-dimensional sphere, the angular momentum sphere. And it's important to appreciate there's a Hamiltonian vector field there, which is what we did on that we certainly appreciated that on that homework assignment. We talked about that vector field. Okay, now at the end of our last meeting, we examined two equilibria. There's a stable equilibrium here at the center of the picture, and we looked at the vector field near that stable equilibrium, and there's an unstable equilibrium here at this location where phi is equal to pi. This is the location where the pendulum is balanced upside down. So you can certainly do that in classical physics, have the pendulum perfectly balanced upside down. So the thing is pointing straight up, vertically upwards. The angular excursion away from the lower equilibrium is pi, so that's 180 degrees. This is an unstable equilibrium. And the motion we talked about last time, the so-called stable and unstable manifolds, you can prepare the system so it is initially at a location on the separatrix that's very close to this equilibrium, but slightly displaced away from the equilibrium, and that will grow exponentially, moving off to the right like so, and ditto going the other way. There are also solutions which asymptotically go towards this equilibrium point. And those are cases where you have prepared a pendulum with just enough energy to get to the top. In other words, the total mechanical energy is equal to the mechanical energy at this location, which we've marked with a dot. It takes infinitely long for the pendulum to get there. So those observations are apparent in these diagrams here. Okay, so we started by looking at the situation near the origin. So that's this location here. And now this time we did draw the vector field because we want to actually see those arrows. And what is this vector field? Well, here's the formula, right? Remember this construction, let's appreciate where this vector field came from. This vector field came from an equation of motion. Okay, let's indicate. So here's the title of this little box, EOM. This is the equation of motion that is valid if you're near the origin. If you get further away, we have the nonlinearity, right? We have the sine of phi rather than phi. But if you're near the origin, then the sine of phi is approximately equal to phi. And we have this wonderful equation. Of course, this omega naught is a constant. So it has the structure of the acceleration equaling a negative constant times the excursion. And so this is the equation of motion for a simple harmonic oscillator. All right, another wonderful three-letter abbreviation. I see there's something in the chat window. Sorry, I missed it. And now in Windows, I can hover, and this message, 1248. Okay, I didn't snooze too long there. Okay, great question. How do we determine if something is stable or That's an excellent question because you may be looking at that question on the final exam. So the question was, how do we determine if something is stable or unstable? Let's take a second to talk about that. Okay, so what I'll do is, I'll write it down at this location here. Okay, so let's analyze this very general question. How do we tell if something is stable or unstable? Okay, so the big picture is we start our discussion here. If you have an equilibrium, okay, what does that mean? The sum of all the forces is 0. So we can write very compactly like this. The sum of the forces is 0, okay? And the solution, okay, is that the configuration okay, So that's the starting point for our discussion. What does it mean to have an equilibrium? Well, the sum of all the forces vanishes. For example, this pendulum balanced upside down, that's an equilibrium. You've got gravity straight down. And the pendulum rod now is a rigid object, and it's able to exert a force upwards on the little mass at the end of the pendulum. So the sum of those forces is 0. So again, that's the notion of what is an equilibrium. Now, an equilibrium can be stable or unstable. Okay. So the question is, if you have an equilibrium, how can you tell is it stable or unstable? Okay. So here we examine the behavior of the system near equilibrium. Okay. So we study okay. So to decide, is this thing stable or is it unstable? What we must do is study the system near the equilibrium. And quite generally, we have this technology in chapter 11. Okay. What we do is we do an expansion. We use our fundamental skills in terms of power series expansion. We have the binomial series, etc. We know how to do small angle approximations. So here's our textbook. And here's the inside front cover. And it's challenging, but I can position it onto the document camera. I don't want to bump the document camera. Yeah, it's very challenging actually to do this. Okay, so we have the binomial series, and we have our various other, we love this series with a sign, etc. So we can look at the equations of motion near equilibrium, okay? And so you will have oscillations. The two possibilities are oscillations or exponential growth. So, and here there's a finer point. Let's appreciate the finer point. When we say exponential growth, there is also exponential decay. So in terms of the word here, unstable, we're really thinking of this exponential growth. But there's also exponential decay. All right. So it's useful that we understand this from the perspective of chapter 5, right? Chapter 5, what we did, we had a certain ansatz for a differential equation, right? We looked at the equation and in the case of exponential growth and decay, we would have e to the lambda t and e to the minus lambda t. These would be the fundamental, these two functions of time really capture the behavior. And for the oscillations, we would have a sine omega t and a cosine omega t. Okay, so this is in answer to the question, how do we know if something is stable or unstable? This is kind of the big picture. We start with the equilibrium, and oftentimes people get tripped up when they say equilibrium. For example, if you, in classical mechanics, you can balance a pencil on its point, right? And it will just stay there. In quantum mechanics, you know, eventually it must fall over because of the uncertainty relation. But in classical mechanics, you can balance a pencil perfectly on its point and it will stay there. And sometimes when people describe this, they get tripped up and they say, yeah, it's motionless. It's just sitting there. It's stable. Well, it's not stable. It's true that it's motionless. And that's this statement here. The configuration is a constant as a function of time. All right. As a function of t, it's constant. And so here's this pen cap. In principle, I could balance this pen cap. Of course, you know this is going to be difficult. I can cheat. You see the end of it is flat. Why don't I just, even that is going to be challenging. Yep. But you see my point. You could balance this pen cap. And often when people describe that, they say, yeah, you've balanced it. It's perfect. It's motionless. It's stable. No, it's not stable. Stability is something else. It's motionless, yes. And that's this statement here. The configuration is a constant as a function of time. That's a solution. And in our picture here, we have these special points. There's a special point. That dot is a solution to the equation of motion. And it's a solution where phi is a constant, in this case 0, and phi dot is a constant, which is 0. Over here, phi is a constant equal to pi, and phi dot is 0. Again, that's the solution to the equation of motion. And that's true for all of these. You see, we have a sequence, an infinite sequence of equilibria, and they alternate. Stable, unstable, stable, unstable. So to answer the question, how do we decide is it stable or unstable? You see how that brings in some important topics. We have chapter 11, we have chapter 5. And so the short answer is you analyze the equations of motion near equilibrium. This is going to require some series expansions if you have some arbitrary equation of motion, right? We have a variety of techniques. And we saw in chapter 5 that the solutions for these kind of problems, you'll have either exponential growth and exponential decay with a real lambda. Yeah, alternatively, you have the oscillatory behavior. The simple harmonic oscillator gives you this structure, sines and cosines of omega t. If you reverse the sign of the spring constant, then you have these two solutions, the exponential growth and decay. Okay, yep, great question. It's always good to bring in those concepts. Okay, so returning to this analysis, okay, in the spirit of that discussion, let's now revisit the equation of motion. This again is the simple harmonic oscillator, and that is chapter 5. Right. We know how to solve this. We get the sines and the cosines. And so if you write down that solution, for example, phi is equal to some amplitude, which is small, times a cosine omega t, and then you plot that, you'll go around in this picture like so, right? If phi is the cosine, then phi dot is a negative constant times a sine. You work it all out. We're going clockwise in this picture. Okay, the important thing is to appreciate that this equation of motion, right? This is a second order differential equation that governs the evolution of the system. That's an equation of motion. And in this discussion, we want to appreciate how it defines a vector field on this two-dimensional space. And again, that's the fundamental equivalence here between the Lagrangian worldview and the Hamiltonian worldview. You can take this equation, which comes from a Lagrangian, right? We know Lagrangians produce second order differential equations. And this equation in the box here is a nice example of an equation of motion. You can get this from a Lagrangian. It's also useful that you can cast this same equation in this form here. And you see we have first order differentiation of a vector, which is constructed in the following way. It's a two-component vector with a phi and a phi dot. So when you compute the first derivative of this vector, the upper component is phi dot. So we just write the phi dot there. And the lower component is phi double dot. And phi double dot is equal to this minus omega naught squared phi. So it's this construction here. And it's the kind of the realization, the fact that we prefer to view this as a vector field defined on this state space. It's this precisely this vector field here. We've used the lowercase v. This is the vector field. It's your velocity in state space. So if you choose any point in this picture, you know that the system in state space will move at that location according to this velocity vector. So this is a vector field. It's a static vector field, right? At every point in this diagram, you could draw the vector field. So here we've actually drawn the vector field near the origin. They circulate around like so, and you can read that off here. For example, if you're in the upper right portion of the picture, the so-called first quadrant, both phi and phi dot are positive, And so this vector has a positive first component and a negative second component. So you see it kind of slopes down to the right. Okay. And so the same construction works everywhere in the picture. It's useful to observe that this vector field can be written as a constant matrix times your position vector in the diagram. Right? That particular structure is something that you cover in Physics 89. And the problem is equivalent to exponentiating this 2x2 matrix. So that's a bit of an optional remark. To solve this equation, which has the structure that the time derivative of a vector is equal to a constant matrix times the vector, you can solve this using techniques from Physics 89. You would compute the eigenvalues and eigenvectors of this matrix. Certainly doable, but you can also solve it using chapter 5, right? Because this structure here, that the time derivative of the vector is a constant matrix times the vector, it's fully equivalent to this equation here, which is a second order equation. And this is what we solved in chapter 5. Okay, so now let's look at this equilibrium here. That dot, you see, I drew a very pronounced dot. That's an equilibrium, right? This dot represents the pendulum upside down, balanced perfectly. Now, what happens if you're nearby? What's the behavior of the system nearby that dot? Okay, and so what I'll do is, can we, it's a question of, can we fit this on the document camera? And the answer is, it's time for some origami. Here we go. Okay. So got a few more writing implements. Let's remove some of this debris over here and really get this nice and cleaned up. Okay. So there's my origami project. So what's happening here is we're going to examine the behavior of the system near this point. Okay, and that's the title here. We have phi comma phi dot. That's our location in state space. Near this point, pi comma 0. That pronounced dot is pi comma 0. That's an unstable equilibrium. Let's appreciate why this is unstable. Well, we drew the vector field. How did we know that that was the vector field? Okay, the answer to that question is we have phi. Remember, the basic premise is we are near this location. So we'll use one of our foundation principles. This is something we did in the chapter 7 as well. We have an equation like this. This is very streamlined notation. What does this mean? Well, if you exhibit the arguments explicitly, this is phi as a function of time equaling pi, that's a constant, plus epsilon. Right? Remember, we had this in the chapter and on the homework. So this is the same statement now with some more explanatory details added to it. So the statement is that phi is a function of time. It is equal to a constant pi plus a small function of time. Okay. And then you plug this in, you use a trigonometric identity. We need to know the sign of phi of t. And now there's a so-called angle addition formula. The sign of pi plus an angle, this is minus the sign of the angle epsilon. Okay, and now we bring in the assumption that this word, keyword here, near, that's a keyword. So epsilon is small. The sign of a small angle is just the angle itself. So this is equal to minus epsilon of t. Okay, so having said that, we can draw this picture, the unstable manifold. It would be better to write this as You see that's the phi. We subtract the pi like so. Okay, so this horizontal axis is epsilon, and we certainly have epsilon equal to 0 at the center. The vertical axis phi dot is equal to epsilon dot. Okay, so having said that, we can write down the vector field just as we did in this, right? Just as we did in the previous example. We write down the vector field. The upshot is the sign reversal. There are some sign reversals, and the structure is this nice hyperbolic structure. The streamlines here will be hyperbolas, right? Whereas here, in some sense, they were ellipses. Remember, the two axes have different units, so it's not proper to say that this is a circle. That would be something you could say if the two axes had the same units. But if the two axes have different units, typically people say it's some sort of generalized ellipse. Okay, so the vector field looks like this, and you see we have the exponential growth, okay? Because these vectors are getting longer and longer. That's something I should emphasize, like so. So near the center of the picture, the vectors are small. That's also true here. The magnitude of these vectors near the center is small, and the magnitude goes to 0 as you approach the origin. The same statement is true here. As you approach the origin, the magnitude of these vectors gets smaller and smaller. The same statement was true when we looked at the angular momentum sphere. We had the intermediate axis theorem. We had Euler's equations. They gave us a vector field on that angular momentum sphere, and we had the intermediate axis. This same picture emerged in that case. So that's something we'll talk about later today in our review session, which is later in today's lecture. Okay, so here, the result, the net takeaway message is we have a sign reversal here, and though it's simply the reversal of a sign, you see we have a fundamentally different structure. Here you have these circulating streamlines. Here the streamlines are hyperbolas. They go off to infinity. So that's the crucial thing with the unstable growth, the unstable equilibrium point. We have exponential growth. These streamlines, if you sketch the streamlines, they would go out to infinity. Of course, in the original diagram, the streamlines don't go out to infinity because our analysis near, when we did the so-called linearization of the problem near this equilibrium, we were looking at the behavior, the structure here near the equilibrium, okay? For the actual problem, the streamlines don't go off to infinity. They go zipping over here, and then it turns out that the structure of the vector field is different here. The linearization, this linearization, right, this simplified description of the vector field, this was valid near that critical point, all right? And the statements that we make about this system, we make statements such as the streamlines go off to infinity. That's really only within the context of this linearization, okay? But for the actual problem, the streamlines don't go off to infinity. It turns out the vector field in this region is different than for the linearized problem, and the streamlines go over here, okay? So the motion of a pendulum, which is, let's say it's not 180 degrees away from the lower equilibrium. Suppose you started at 179 degrees. So it's nearly vertical. You let it go. What does it do? Well, you've started it here. If you start it from rest and you started from a point with phi dot equals 0, it slowly accelerates. Then it goes quite quickly here. You see the velocity is large, okay? This is when we are at this location, which is equivalent to this location when the pendulum is pointing straight down, okay? And then it slows down and it very slowly approaches the other classical turning point. We've identified these are the so-called classical turning points, okay? So that's the picture there. We have the stable and unstable manifolds, right? And you remember those slides we looked at for the interplanetary superhighway. It was essentially a higher dimensional discussion, but the existence of stable and unstable manifolds is a big part of the discussion. And so it's important that we realize here in this picture, if you prepare the system with initial conditions in this territory, they will move towards the equilibrium point. If you prepare the system exactly on this stable manifold, which I labeled it here in pencil, this is the stable manifold. If you prepare the system exactly here. What does that mean? It means you take a pendulum, you give it exactly the amount of energy it needs to reach that upside down equilibrium configuration, okay? What does it do? It asymptotically approaches it. It asymptotically approaches it in this sense here. Remember the two fundamental solutions from chapter 5, the exponential growth and the exponential decay, all right? So in this picture, if you prepare the pendulum with exactly enough energy to get to the equilibrium where it's motionless and vertical, what does it do? It asymptotically approaches, it gets slower and slower. It never, you could wait forever and it will never get there. It's going, you could check back 400 years from now and it will be right about here, very close, but still not there because it's slowing down. So it's a remarkable phenomenon here that if you prepare the system exactly on this stable manifold, it will asymptotically approach it. If there's a slight error, what does it do? Well, it gets slower and slower. It moves into this territory here where the vectors are very small, but they're not quite zero. So it very slowly moves through here and then zips away. And that was the dancing T-handle. You remember the dancing T-handle, these remarkable videos, and I did post several of them on B courses. When you have the angular velocity very, very close to the number 2 axis, right, the intermediate axis, then on the angular momentum sphere, again, we have a separatrix, and the vector field is very small when you're near that critical point. So the angular velocity vector and the angular momentum vector in the body frame, they get close to that number 2 axis. They reside in that territory for a while, and then they zip away and get faster and faster. So that was this remarkable motion that the dancing T-handle would appear to spin about one axis and then suddenly flip about. Rather quickly, it would flip about and then appear to spin about the other one. If you haven't watched those videos recently, I'd recommend you watch them again. They're on B courses. I did put them in the appropriate homework folder as kind of a motivational thing to look at. The remarkable motion of a free rigid body, right? It is remarkable how complicated it gets. Okay, so with this material in mind, let's talk about the Lagrange points. Okay, these are special points. Now we're in the exciting world of the interplanetary superhighway, right? Which is our future. In case we have to leave planet Earth, right? We got to go somewhere else, et cetera, and so forth. So yeah, the interplanetary superhighway. Let's get another piece of paper, and we're going to continue our discussion here. I'll undo my origami, right? The point was we want to talk about Lagrange points. So here we go. Okay, we're going to talk about Lagrange points from different perspectives. So first, we'll do a calculation, and remarkably, we'll do this calculation using 4 different techniques. We'll look at essentially 4 different chapters in our book, okay? We'll use important material from 4 different parts of the course. We'll solve the same problem 4 different ways. It sounds like it's redundant, but actually it's very useful. When you have these different perspectives, it helps to cement our understanding. Okay, so we're going to study first the following. First, we will consider the case of 2 masses orbiting the common center of mass, right? And you know, we did have a fun sample exam problem, I think for the second midterm. We had 2 stars orbiting the common center of mass. In that case, they were elliptical orbits. But there are some very interesting calculations we can do here with circular orbits. We must understand the case of the circular orbits. Okay, so you have 2 masses. They are orbiting the common center of mass. Let's draw the picture. Okay, so here's the center of mass. And let's draw a picture of the situation in kind of a generic state. So you may have mass number 1 over here. And now let's do this. we want to have a very accurate diagram. So suppose, okay, so here are these two masses. The center of mass is here, so you can see that the mass M1 must be larger, and this is the smaller mass. Okay. For this discussion, we're going to consider circular orbits. So consider two masses and circular orbits. Okay, so this picture was a snapshot. What if you now run the movie, so to speak? This mass proceeds in a circular orbit, like so. And this mass, same thing true here, circular orbit. Okay, so at any instant, and this picture was drawn for just kind of a generic instant. Of course, the center of mass is on a straight line segment connecting the two masses. So this is our picture. All right, as we go through this, we want to be sure that we understand, for example, chapter 8. How would you apply chapter 8 to this discussion? Okay, we have different ways to analyze this problem. So calculate omega. Of course, omega is 2 pi over the period. Okay, and there's the lowercase tau for the period. So we're going to do this in 4 different ways. Here's our first calculation. Okay, it's very useful to understand that there are 4 different ways that we can, there are at least 4 different ways we can use material from our course. All right, good old Kepler's third law. Let's talk about Kepler's third law. Okay, now Kepler's third law, as you know, we have 2 formulas. We like both of these formulas. There's the exact formula and there's the approximate formula. Okay, you remember the exact formula and the approximate formula. All right, so let's get the textbook. Equation 854 was the exact result. Okay, so again, this one is exact. Equation 854 is exact. And this one, you see it's more popular. It earned a gray box. You have to be an amazing formula if you want a gray box. However, this is an approximation. The reason it's wildly popular is because of the universality. This is a statement, you see m sub s, that's the mass of the sun. For all the planets in the solar system, you have this proportionality, the square of the period proportional to the cube of the semi-major axis. Okay, wonderful result. Let's use the exact result. This is the exact result. Okay, so Kepler's third law, and again, equation 854, that thing is exact. Very nice. Okay. What we want to do when we apply equation 854, we got the tau squared Okay, there's something we have to talk about here. For the circular orbit, A equals R equals a constant. This is crucial that we understand. Obviously, this equation is from chapter 8. Okay, it's equation from chapter 8. And you know in chapter 8, we have an R vector, which is the relative displacement, okay? So you see the mass 1 here, the mass 2 there. The R vector goes from here all the way over to here, okay? And this little r is the length of the R vector. Okay, so you remember in chapter 8, we had the hierarchy. We had 6 degrees of freedom, 3 degrees of freedom, 2 degrees of freedom, going down to 1 degree of freedom. Okay, so we were very fond of drawing pictures. When you get to this problem with 2 degrees of freedom, you know we would draw a picture like this. For the elliptical case, the ellipse would look like this. Okay, this is the plot summary. This is the amazing story we talked about in chapter 8. Okay, it's a remarkable story. And let's appreciate in the chapter 8 summary, you have a formula for this ellipse, right? This is an ellipse. This formula is in the summary. And the appropriate place to talk about this diagram is the 2 degree of freedom problem. We have these 2 axes. We're living in a 2-dimensional space. It's a planar space, 2-dimensional world. And the path of the particle, if you have an elliptical orbit, looks like this. The circular orbit is a special case of the elliptical orbit with 0 eccentricity. So when you say circular, the eccentricity is 0. Okay. And it's important to appreciate that this discussion here, when we say 2 degree of freedom problem, there was a single particle of mass mu, okay? I'll put the mu here just to remind us, when you are in chapter 8, when you're looking at results from chapter 8, there's a particle and it has a mass mu. You are in this territory here. The 3 degree of freedom problem, the 2 degree of freedom problem, and the 1 degree of freedom problem, they have a single particle of mass mu. The 6 degree of freedom problem, I'll draw a curly brace like so. There are 2 particles and they have masses m1 and m2. Okay, so it's important to understand when you apply the results from chapter 8. Okay, and it's an amazing story that starts here with 2 particles, masses m1 and m2, and ends here, 1 degree of freedom problem. You can solve this, no problem, using techniques we studied earlier in the course. So for this amazing story, it's here that we have 2 particles, m1 and m2. So the picture that we drew, this entire picture here, this picture belongs to this part of the story, okay? This picture belongs here. It's the 6 degree of freedom story. And this picture here, which is from the chapter summary, is here, the 2 degree of freedom problem. Here you have just 1 particle, mass mu. Throughout this portion of the story, you have 1 particle of mass mu. Okay, so it's very important to understand that the lowercase r is the distance from this particle to this particle. The lowercase r vector, this vector here, is the relative position of these 2 particles. We never rescale that. Okay, so this r continues to be the distance between the 2 particles. Okay, and using the notation from the book, we would call this R1. Okay, so that's R1, and R2, I'll use gray. Here's the pencil. Okay, so I've used some shading. Maybe someday I'll get a blue pen or something like that, maybe green, then I wouldn't have to shade like that. Anyways, so the idea is R1 is the magnitude of the R1 vector, right? Okay, R1 is the magnitude of the R1 vector. This is important in chapter 8, and there's a figure that really, this is fairly early in the chapter, but it's this figure here. This is figure 8.3, and you see very important construction. There's the center of mass. You have a position vector. The R2 position vector is rooted at the center of mass. There's the origin. So it's a vector from the center of mass to particle number 2. And the R1 position vector, again, it's a vector rooted here at the origin, and it points over here to particle number 1. So right here inside of the figure, we have a useful formula. The R1 vector is a multiple, and this is a number like, for example, 0.9. You see it's M2 over the total mass, so whatever it is between 0 and 1. So R1 is slightly shorter than the R vector. The R vector goes from particle number 2 all the way over to particle number 1. That's the R vector, and it's right there. And the magnitude of that vector is just lowercase r. So lowercase r is the distance from particle number 2 to particle number 1. So that continues to be true in this discussion. Okay, so in this discussion, in other words, if we want to get the right answer using this Kepler's third law, we have to be very cognizant of all these issues. So the little r is the distance from here over to here. So furthermore, we can say this. For this problem, little r is equal to R1 plus R2. Right, that's a statement about scalars. R1 is a positive distance, this length of this red vector, and R2 is the length of the gray vector, that's positive. Positive plus positive equals positive. Okay, so that's this R here. And this is the semi-major axis. Okay, the lowercase a is the semi-major axis. In this picture, it's 1/2 of the major axis. Here's the major axis. I'm going to shade it. That thing I just shaded there, that's 2a. That's the major axis. For the case of the circle, you know, the two foci that coalesce, you just have a center of the circle. And so the crucial thing here to understand is when epsilon is 0, then r is equal to a. Okay. And so that's why we have this form here. If you look at equation 854, you see the semi-major axis, but now we are fully justified in writing this. In particular, you don't want to put a 1/2 of r or something like that. That would be wrong. The semi-major axis here is equal to r, which is the distance from this particle over to this particle. Okay. The diagram as it's shown here has the mass m1 approximately twice the mass m2. So maybe that's 1,000 kilograms. This is 2,000 kilograms. That's an example. Okay, so you go through the calculation, and this cleans up a bit, and we get the GM equals omega squared r cubed. All right, we did a little cleanup. You see we can divide both sides by the tau squared. That is very nice because then you have 4 pi squared over tau squared. That's omega squared. So in that sense, you very quickly get an omega squared r cubed, and then the mu is a product over the sum. That cancels this very nicely, you get the GM. Okay, so here's our conclusion. And that's the first of 4 discussions here. How do you get the omega? It's very useful to really understand Kepler's third law. Obviously, Kepler's third law is a big selling point here for chapter 8. Okay, so here's our next calculation. Let's revisit this problem using Newton's second law. Okay. How would you do this? What if you were taking a final exam and it says use Newton's second law to figure out omega? Okay. Remember Newton's second law, the sum of the forces equals the mass times the acceleration. Okay, sometimes people just write capital F. It's understood that that's the total force. Okay, so for uniform circular motion, okay, what you do is you arbitrarily select one of the masses. Perhaps you'll select mass number 1. Mass number 1 is executing uniform circular motion. It's true that mass number 2 is over here. Let's not worry about mass number 2 for the moment. Mass number 1 is executing uniform circular motion. We know the acceleration for the case of uniform circular motion. The acceleration can be summarized as follows. The magnitude is constant and the direction always pointing at the center. Okay, so you write that down. The magnitude of the acceleration is going to be omega squared r1. If we focus our attention on mass 1, then the magnitude of the acceleration is omega squared r1, right? That's just the result from uniform circular motion. You can prove that using the techniques we have, right? Using vector representations, you differentiate twice, you get this omega squared r1. Okay, and so that's the magnitude of the acceleration. That must equal the magnitude of the force divided by the mass of the particle. Okay, if you write that down, that's a gm2 over the square distance. Again, the interparticle distance is the r. So now it's r squared. Okay, so using Newton's second law, we conclude the magnitude of the acceleration of particle number 1, that's this thing, is equal to the magnitude of the force divided by m1. That's this thing. Okay, and then you clean up a bit. You use the fact that r1, remember that picture we just looked at in the book. I'll show you again. This picture here, very important picture, figure 8.3, page 298. This is very important. This is the glue that sticks together the story, right? That figure helps you to get from the 6th degree of freedom to the, it's very important for problem solving. So this R1 is a multiple of the R, okay? You go through that, you plug in the numbers, you get the same answer, okay? So let's save time by moving on. There's just a little bit of algebra to be done here. The point is you get the same answer. Let's talk about our third approach, the so-called equivalent one-dimensional problem. In chapter 8, we have the so-called equivalent one-dimensional problem. And again, here's the plot summary of chapter 8. When you reach this point here, it's called equivalent because we have this single particle of mass mu. The original problem had two particles, masses m1 and m2. So in that sense, the problem that emerges here is a 1 degree of freedom problem for a single particle of mass mu. It's equivalent to a particle living in a one-dimensional space, a space that is not rotating, just a fixed one-dimensional axis under the influence of two forces. They can both be written as minus the gradient of a scalar. And we have the original force and now this centrifugal, the quote unquote centrifugal barrier. Okay, so this is in chapter 8. We have the mu, r double dot, equaling, right? You see the structure, mass times acceleration minus the gradient, the ddr, that's the gradient in a one-dimensional world, of an effective potential. Okay, that's equation 829. Okay, and so for the case of a circular orbit, this r is constant. Remember, that's the interparticle separation. That's simply a constant value. So the second derivative is certainly 0. The first derivative is 0. We've got a 0 on the left. Therefore, we're at a minimum of the effective potential. What is this effective potential? That's why this is called the equivalent 1 degree of freedom problem. This effective potential is U of R plus the centrifugal term remember, the centrifugal potential has the R squared. Therefore, when you differentiate to get the centrifugal force, you've got an R cubed downstairs. So this force dominates. If this U is a gravitational problem, then this centrifugal barrier prevents the particle from getting to the origin. Okay, and the important thing to understand here is that L, right, again, with reference to our plot summary, when you have this single particle of mass mu, living in a world here for the 3 degree and for the 2 degree of freedom problem, it lives in a world where the origin plays a special role. There's a force center. Okay. In the 6 degree of freedom problem, the origin played no special role. But for the 3 degree of freedom problem, 2, etc., the origin plays a special role. There's a force center. Okay. And we compute the angular momentum of this single particle mu about the origin. The magnitude of that angular momentum is equal to the angular momentum of the 2 original particles about the center of mass. So this picture here is perfect. We need to know the angular momentum of these 2 particles, the total angular momentum, about the center of mass. And we can compute that easily because we know that these distances are constant. We know that this omega is constant. Okay. So the upshot is we can compute L. You've got this M1 R1 squared. You recognize this as a moment of inertia plus M2 R2 squared, right? That quantity in parentheses, that's the moment of inertia times omega. Okay. And you can rewrite this. This is mu times R squared. Again, you get that from this wonderful picture, right? This is very important to understanding chapter 8. And inside of the actual figure, chock full of useful information, right? So you plug in, when this cleans up, you have the reduced mass times R squared times omega. Okay, so this will clean up rather nicely. And the upshot is you can compute omega. Once again, I'm just going to point at this box. You get the same answer, but the important thing is to understand the ingredients here. And again, this exercises our knowledge of important stuff from chapter 8. But not only chapter 8. Let's solve this. Here's item number 4. We're going to solve the same problem using a different method. We're going to solve the problem in a rotating frame. Okay, so chapter 9. Now we're in chapter 9. We have to be careful because the notation in chapter 9 is different. You have to be very careful. Okay, so that's part of the reason we're going through this. The different chapters have different notation. You know, in chapter 8, the lowercase r vector is an interparticle separation vector. It's a vector that takes you from one particle to another to the other particle. In chapter 9, this symbol is again a reserved symbol, but it's reserved for something else. This is the position of a particle in a non-inertial frame. Okay, so as we go into chapter 9, we're going to solve this problem in using chapter 9 technology. But let's be very careful with the notation. Okay, so how would you discuss this in chapter 9? You would draw a picture like this. You have the center of mass. Let's have the origin there at the center of mass. We have these 2 particles, and the really cool thing is they're simply motionless. Okay, so we're drawing a picture for the S frame. Okay, so if we want to use results from chapter 9, then this is the picture of the experiment that we're talking about. We are in a non-inertial frame. The S frame is a non-inertial frame. And the problem is very simple. You have a particle here, it's motionless. You have a particle here, it's motionless, and they remain motionless. So it's remarkable that you have two particles and they're simply motionless. Okay, so we must explain what's going on here. How can we do this? Well, remember the original problem, this was the picture. You have these two particles orbiting the center of mass, and we use the lowercase omega for the angular velocity of these two particles. They're orbiting the common center of mass. Obviously, they have the same angular velocity because you have at all times a straight line connecting the two particles and going through the center of mass. Okay, so lowercase omega was the angular velocity that we used in this discussion here. Now in chapter 9, we like to use capital omega for the angular velocity of the S frame relative to an inertial frame. Okay, so if we're going to use results, from chapter 9, then we need to look at chapter 9 and what we called omega before. Now we're going to call that capital omega. Okay, so with that in mind, here's this picture of the actual physics in the S frame. Two motionless particles. We love that because then the Coriolis force is 0. You're in this S frame, it's a rotating frame. If there are moving particles, they're going to experience a Coriolis force. But both of these particles are motionless, so the Coriolis force is 0 on both these particles. That's wonderful. There is one inertial force, and that's the centrifugal force. Okay, so we do have our centrifugal force, obviously in the chapter summary. And here's where I want to take a moment to explain the dangers of the notation. Okay, if we simply jot down the formula from the chapter summary, we're going to get in trouble. So here is what we have. We have the mass of, quite generally, the mass of a particle. We have the omega vector perpendicular to the page, cross. And now for clarity, I want to say some more about this lowercase r vector. We're looking at equation 936, so I'm just going to call this 936. R sub 936, okay, I'll explain that in a moment, cross omega. Okay, so we want to use this result from chapter 9. It's equation 936. Okay, here you go. This is chapter 9. This is one of the results in chapter 9. Notice we have a lowercase r, but we're going to get in trouble here because we have been using lowercase r in chapter 8 for something else, the vector from one particle to the other particle. Here in chapter 9, there's only one particle. It has a mass m. Okay, this is the centrifugal force on a particle of mass m in the reference frame S. S as in Sierra. Okay, and r is the position vector, okay, of that particle in the S frame. So that's the crucial thing here. This r vector in equation 936, this is the position vector of the particle whose mass is m. It's the position vector in the non-inertial frame. Okay, so that's what's going on here. And this is our formula for the centrifugal force. Okay. So the situation in the S frame is we have these two particles, they're motionless. They experience gravitational forces, and you can compute the gravitational forces using the familiar results. You look at the distance between the particles, that's going in the denominator raised to the second power. We're talking about Newtonian gravity. So we can figure out the gravitational forces, no problem there. They both experience centrifugal forces. And the crucial thing now is when you compute centrifugal force, you must look at the distance from the axis of rotation. The axis of rotation, I must be careful with my pen here. The axis of rotation is perpendicular to the page, and I'm indicating that here with this spectacular view of the pen perpendicular to the paper. The document camera does a good job of capturing that. That's our axis of rotation. And you know the centrifugal force is proportional to your distance from the axis of rotation. So that's the sense here of this equation. Okay, so if you write that down, in particular, choose one of the particles. You can figure out the centrifugal force, right? You have this distance from the origin to the particle. You have the square of the angular velocity, and that's balanced perfectly by the gravitational force. Again, for the gravitational force, you use the distance between the particles. So the magnitude of the gravitational force, capital G, the product of the two masses, and then you must divide by the distance between the two, right? That's what we were calling little r. Okay, again, I'll simply point to this box. You get the same answer, but the crucial thing here is to be very careful with the notation. So we have a question in the chat window. I'm always curious, when did the question came in at 1:45, that's right, pretty much immediately just came in. Is omega constant in the rotating frame? Great question. In chapter 9, we have two reference frames. So there's an S0 frame and there's an S frame, okay? And there is relative motion, right? The S0 frame, you can think of that as being the so-called fixed stars. In astronomy, you talk about the fixed stars, and that's the way to emphasize that it's a reference frame that's not rotating. And this S frame is rotating. So yeah, in chapter 9, this omega vector is a constant. Okay, and we just quoted a formula, and as you point out, there was a private message in the chat window. This omega vector is a constant, okay? It's the same omega vector, and again, it's perpendicular to the page. I'll be careful. It's perpendicular to the page like so, and it is a constant. And so to make a connection with this result here we were using lowercase omega. That now plays the role of the capital omega. Yep. Okay, great. So there are some other topics we want to talk about looking ahead to the final exam. Let's talk about the Lagrange points. Okay. So this discussion here, you see we have chapter 9. We're in a rotating frame. There are fictitious forces, sometimes called inertial forces. Okay. So here's the fascinating story with the Lagrange points. Okay, so we'll continue that discussion. Here's the picture in the rotating frame. So this is in the S frame. Okay, again, we have the center of mass. Let's put it here. We have our particle number 1. Here's M1. And we have our particle number 2. Okay, and the really wonderful thing about the S frame is that these two particles are motionless. Okay, we're thinking about, for example, the Earth and the Moon, or you can also think about the Sun, that's the more massive one, and the Earth, these kind of problems. So for simplicity, we've chosen to look at the case where they have circular orbits about the center of mass. And now the researchers studying the interplanetary superhighway, they must deal with the fact that the distance between the Earth and the Moon really is not a constant, right? We have some eccentricity. It's not a perfectly circular orbit. The Moon's orbit about the center of the Earth is not a perfect circle about the common barycenter. Anyways, so that's another complication you have to deal with. And again, I'd advocate taking Physics 205. But for this discussion, let's treat the case where M1 and M2 are enjoying these wonderful circular orbits about the center of mass. So in the S frame, these two particles are just motionless. Now the question is, what if we introduce a small test particle? Okay, we're going to have a small test particle, and we're going to place it in this picture. Okay, so it's useful to think of these as massive things such as a planet and a moon. Okay, so here's a planet and a moon. They're massive. They are not affected by the motion of this little test particle. This could be a human-made spacecraft. Okay, so what happens? Well, let's examine some locations here. First, let's do some experiments where we think about this particle as being motionless. So M, motionless. Okay. So for the Lagrange points, we ask the question, can we find solutions here in the S frame? You place a little test particle and it remains motionless. The important thing is this is a small particle, and so it has no impact on these large objects. Here's a planet and here's a moon. They are unaffected by the test particle. Okay, so they continue just to be motionless. And the question is, can we place a test particle in this picture? So before we set up the math, let's use our intuition to understand that there will be multiple solutions. I'll use a different color. There will be one solution here. I'm using red for the solutions. Okay, so these Lagrange points, I'm gonna indicate them in red. So I circled this with red ink. There's a Lagrange point here, and historically that's called the L1. There's a Lagrange point here, and historically that's called the L2. L is for Lagrange, it's not for angular momentum. Okay, and there's another one over here somewhere, let's put it here. This is the L3. And in fact, there are two others. There's the L4 and L5. They're going to be more complicated. They are not on this straight line that we just drew. They are quite a distance off, and you have these large triangles formed by the Lagrange points. So those are called L4 and L5. But let's begin by thinking about these Lagrange points here. So what's happening is, remember, if you place a test particle somewhere on this axis, it experiences a gravitational pull from mass M1 and M2, and it also experiences the centrifugal force, which is away from the center, right? The axis of rotation is right here. This is our axis of rotation. And so as you contemplate these red dots, these are places where we're going to put the test particle. Just remember that there is a force pointing away from the center of mass, and it's proportional to your distance from the center of mass. So if you place a red dot very far to the right, I'll kind of indicate it like so. If you place a red dot very far to the right, it's going to experience a huge centrifugal force and a greatly reduced gravitational force. So if you place the point too far to the right, it's going to escape to the right. At least initially the force is to the right. Okay, on the other hand, if you place it too close, if you place it very close to this mass, the black mass, then it's going to experience an extraordinary gravitational pull to the left coming from this mass, and that will serve to have a net force to the left. So you can see, just using your intuition, that there must exist a Lagrange point L2 somewhere to the right. And so in this picture, I've drawn the point here. Again, this is the red ink for the Lagrange point. You can go through a similar argument for this one, the balancing the forces, and a similar argument here. So that's using our intuition. So let's talk about a fundamental skill that you can use on the exam. When you have a collection of forces, right, we have to think about these forces as vectors. Sometimes it is useful to talk about the components, for example, x, y, and z components of the vectors. Other times it's useful to talk about the magnitude of the vector and then provide a verbal description of the direction. That's perfectly okay if you specify the magnitude of the vector and verbally state the direction. Okay, so let's do that here. We're going to look at the forces on M. What are the forces on the little test particle if we place it at this Lagrange point here, L1? Okay, and so here we go. We have a list of forces. So first of all, there's a force, we're going to state the direction verbally, a force to the left, right? And that's the gravitational pull due to this mass. Okay, so I stated the direction verbally. The magnitude is G, M, M1 over the distance from this Lagrange point over to mass number 1. Okay, let's say that this distance here is d. Okay, that's the definition of d. So what's the distance from here over to here? That's going to be the r1 plus r2 minus d, and we must square that. Okay, so again, the text tells you the direction, and this is the magnitude of the force. There's a force to the right. It's the gravitational pull from this mass m2. So that's g little m2, and the distance is simply d. So d squared like so. And now the centrifugal force. Okay, the centrifugal force is to the right. Remember, the origin is here. The centrifugal force points away from the origin. You could do a bunch of cross products, but it's simpler just to state it verbally. To the right. What's the centrifugal force? It's m omega squared times the distance from the origin to this point. And that's going to be the r2 minus d. And that's raised to the first power. Okay, so those are the forces acting on this particle. The sum of these forces as vectors must be 0. That means the sum of these two pointing to the right must equal this one pointing to the left. Okay, the result is a quintic equation. Right, a wonderful word, and it is a wonderful world as well. A quintic equation, that's a 5th order equation. I'll put an exclamation point because that's been one of the themes of the course, the fascinating problems that emerge as we solve, as we face mathematical problems that come from the physics. So to find this Lagrange point, we want to find that Lagrange point L1, we must solve a quintic equation. Okay, that's very challenging to do. What we can do is an approximation. Okay, if you have something like the Earth and the Moon, and this is relevant for the L1 gateway. Remember, the researchers working on the interplanetary superhighway, they're advocating the L1 gateway. If it's true that M1 is much greater than M2, okay, so if this is the Earth and that's the Moon, this is a good approximation. Then you can do an approximate solution, right? In general, a quintic equation is rather nasty. The only thing that's easy to solve is a quadratic. That's 2nd order. Cubic, already very unpleasant, etc. Quartic, things get pretty bad. But in this special case where M1 is much larger than M2, you can solve, and you have this wonderful result. D is roughly equal to R2 times the cube root. We have a cube root, even though this is a quintic equation, we have a cube root here in the solution. M2 over thrice, that's 3 times M1, and it's the cube root of that. Okay, so this quantity in parentheses, that's a pure number, right? It's the ratio of masses. We're going to take the cube root, right, and multiply by R2. Okay, so if you ever get lost and you need to find the L1 gateway, just get a piece of paper, plug in the mass of the Moon, the mass of the Earth. This is the distance from the center of mass, the common barycenter that's still inside the Earth, etc. You can find the location of that gateway. Okay, wonderful. So that brings us to the end of the hour. And today is our last lecture. Obviously, the final exam is tomorrow. I do have office hours this evening at 8 p.m. Otherwise, it's been wonderful working with you. It's been a very enjoyable course. And good luck on the final exam. So I'm going to stop the recording. I'll stay here for questions.